Hello, we're going to take a look at some one-dimensional motion information right now, and it's kind of fundamentals. We're going to look at how we can basically track where something is and how long it's taken to get to that location. We're not going to go through all the definitions of the terms here, things like position, time interval, distance displacement. We're really just going to use some of the common language that everybody's familiar with. And if we need to add terms or if we need to modify things later, we'll go ahead and do that. But to start with, we need a couple different ways of visualizing motion. And I usually like to say that if you talk to a 5-year-old and you give them a little picture of a car, this is the world's best drawing of a car, how would you show that that car is in motion? Well, first off, they'd want to know which side's the front. So let's say that there's the headlight and the antenna. Cars don't really have antennas like that anymore, but it's all right. They would probably start by saying, oh, well, you got to draw some speed lines. Vroom, vroom, maybe some smoke on the tires. That works. It gives the illusion, but it's not really scientific. So it's not going to link up with some of the things we want to be able to measure and do calculations with. So two things that we can do are make motion diagrams and make position versus time graphs or position time graphs. And these are in the ascending order of difficulty, but they're also in the ascending order of usefulness. So motion diagrams are pretty easy to do in terms of visualizations. Position time graphs, a little bit more complicated. And they're more complicated, but they're also more useful. They yield new information. They allow us to do all sorts of complicated mathematics later on, especially for AP classes, do some calculus stuff. But it's always a good idea to evaluate something that if it is more challenging, it should also yield more. It should be more useful. If it's more challenging and it's not useful, you probably shouldn't do it. You should probably stick with the easier thing. So we'll start with the motion diagram here. Scroll down here to the info on that. Motion diagrams, sorry, let me get that right where I want it, right in the middle. Essentially are dots placed on a number line that represent the location of an object, and the dots, because you're on one dimension, you can only have one quantity that you're varying, the position. Those dots need to be at equal time intervals. That's really important, and you usually want to indicate what the time interval is. Most examples, it's like every 1 second or every half second. For us, we might do every 1/10 of a second. I got a little example going here, but we got a number line. I've got some numbers on it. Let's go ahead and take a look at a video of a object in motion and see what it looks like. So here I've got a video I shot countertop. There's a multicolored bouncy ball. I've rolled down a ramp so that it's got some speed. And I've got a meter stick where each of the numbers here represent a centimeter. So 1 through 10, then 11 through 20, and so on. And I've got a stopwatch running on my phone because it's a nice, good screen to see. And that's going to tell us the time that the object is at the location. And we can always subtract like the starting number, but we've got a time and we've got a position. We can look where the ball is and we can look at what time it was at the location. That's what we want to use for the motion diagram. So to start, the ball in between frames here, if I go 1 frame forward, it's kind of far forward. If I go 1 frame back, it's way off there. So let's go ahead and say that this is roughly when it's at the 0 position there. So let's go ahead and put a dot on our number line at the 0 position. Use a red dot here. And I'm going to say that that was at time, lowercase t for time, is 11.54 seconds. That was the time, right? 11:54. Now, if I click play, and we see this ball travel across the screen, you can see that it goes kind of quickly across the screen, but the time went up as the position changed. We want to be able to measure those things. So I'm going to go back a couple frames here. We're at the 11:54. It didn't take even a second to get all the way across the screen there. So to get the positions, we need to kind of demark where the object is. So I'm going to go forward a little bit here. Let's say to see if we can get to like 64. That's 65. That's close. And we were kind of towards the front half of the ball, so it's about 5.5 to 6 centimeters. Let's make a mark. So 2, 3, 4, 5, 6-ish. That's where we should be at the next tenth of a second. So I'm going to say by 0.1 seconds. So that's our time interval. Now, generally we wouldn't use tenths of a second, but it's really hard to get something moving slow enough and over a long enough distance and videotape it. So we're going by tenths of a second here. Let's go ahead and take a look at the next tenth of a second or so, to about 74 or 70. Let's go ahead and go back here, I guess. So about 11.73, it's another tenth of a second forward. We can see it's around the 11 centimeter mark. So I'll put a dot at about 11 centimeters. It's going to be a little hazy because we are kind of fudging the numbers a bit. Go forward to about 84-ish, or 85. We're about 16 and a half to 17. So 11, 12, 13, 14, 15, 16 and a half-ish to 17. That's right about there. And you might start looking at that motion diagram and noticing something about the spacing of the dots. Just kind of keep that in the back of your head. Let's go forward to about 94-ish, 95. So we're about 22 and a half. You might be thinking also right now, wouldn't it be great if there's a more accurate way to analyze videos like this? Don't worry, there will be. So let's go. We were at 20. Oh, geez, I lost track of talking over myself. About 22 and a half. So right about here. So again, every tenth of a second, it seems to be pretty equally spaced. It might be important later. Oh, wait, hold on. Supposed to be at 94. Yeah, there we go. Sorry, I was getting a little befuddled there. So then we'll go up to another tenth of a second, about 12:05, and we're about the 17 and a half, 18, and 27 and a half to 2018. That's right about here. And we're kind of running out of space on the number line. So we'll go ahead and call it there. So we've got what seems to be sort of equal spacing. Sorry, that was really sloppy. So the physical distance the ball moves every one of those little time intervals seems to be about the same. Well, it's kind of what we would say that if something was moving at a constant speed, that the distance traveled every second would be the same, so every tenth of a second should also be the same. Now we could go on and get into more detail if we had better tools, which we eventually will, but let's go ahead and take a look at what that would be on a position versus time graph. So for a position versus time graph, not just a motion diagram, we're going to add in a extra dimension. We're going to add in time as a measurement and a variable in our actual visualization. So here we're going to borrow all the data that we already had from before, while it'd be, I guess technically prudent to go back and remeasure everything. Let's not go ahead and do that. Let's just go and use what we already got. So what I want to do is actually create like a little table here. Now, we want to measure positions and times for an object relative to some origin. So we're going to call the beginning of the meter stick the origin, 0 position, but we're also going to call that 0 time. And we want to plot all that data, times and positions, on an XY style graph. So I've got a little coordinate axis here, first quadrant. Now, this will make a lot more sense in the future, but for now, we want to put time in seconds on our horizontal axis, and we want to put the position of the object on the vertical axis, measured in this case, it's going to be in centimeters, and X is what we use for position because X marks the spot. Where is an object? It's at X. So that's, in this case, it's going to be in centimeters. And let's go and scroll back up to our data here because we want to make a little table. I've got my position on my little motion diagram there. Next to my XY graph, I'm going to create a little table here for time and position. Now, the times are going to be 0, 0.1, 0.2, 0.3, 0.4 seconds. How many did we get there? 1, 2, 3, 4, 5.5 seconds. And we're going to record what the positions are there in centimeters. So the first one would be 0. The second was it, we said that was about 6, right? So that's 6 centimeters. And then we got about 11. Then we had, I think I put that like 22 and a half. All of a sudden I got really, precise on my measurements. Then on the, wait, I seem to have lost a dot there. Oh yeah, I did. What do you know? I know some of you were watching this video saying like, no, you forgot about this little dude right here. What about him? I don't even know what that is. That's 17 and a half. What is that? 16 and a half? Yeah, 16 and a half. Then we had 22.5, and then we had about 28. So if I've got those numbers now, and recall I'm going by 0.1 second intervals. If you had a really, really good set of data, what you would have done is right here, you would have zeroed your timer and started at exactly 0 seconds once the ball was at 0, but you can't do that. I'm only one man, right? So as it's rolling, we had to kind of artificially reset our timer to 0. So I'm going to go ahead and plot this data. Each of these ordered pairs becomes a dot on my graph. So at 0, 0, I would have a point. 0 time, 0 position. Well, now I need to set up the rest of my numbers, right? I got to have my axes all set up, so I got to go 0.5 all the way. So let's say that's 0.1, 0.2, 0.3, 0.4, 0.5. Then I got to go up to all the way almost to 30. So let's say that's 10, 20, 30. This would be 5s. 1, 2, 3, 4. 1, 2, 3. 4. This does not have to be good. In fact, I might just fast forward this. So now I can plot all the data points, and we can go ahead and take a look what the graph looks like. Could really use a ruler. Should also label them too. Okay, so that was a lot of work. But we're looking at it, and geez, it starts to look kind of like a straight line almost. So if I were to, I don't know, draw a straight line through all this stuff, like so, maybe it's not perfectly straight, but it seems like there's some straight linedness to it, right? Go ahead and kind of move it over here, do like a best fit or something like that. Seems like there's maybe just like one outlier there, but overall, it's a pretty linear relationship there. And that's something else that we're going to explore. I realize this video is kind of going on for a bit. The idea of something moving at a constant speed, where we can look at the motion diagram and say, like, seems to be going equal intervals of position every equal interval of time. And then if on a position time graph, it looks like a straight line. It's going to be very important. We can do a lot with that. So here's a question leave you with. If the object were rolling faster, what would the motion diagram look like? And what would the position time graph look like? The motion diagram might be easier to think of. Position time graph might take a little bit more thought. So we'll leave you with that, and hopefully this was helpful.